The core elements of the universe, the tiniest, indivisible components of all matter, known as elementary particles, form the basis of everything in existence, from a speck of dust to sprawling galaxies. Yet, despite being so fundamental, they are famously hard to detect and even more challenging to comprehend. These entities don't behave like anything we encounter in daily life, and our usual way of thinking falls apart when we try to visualize them. To grasp the true essence of these basic particles, we must venture into the bizarre and mind-bending world of quantum physics. At its essence, an elementary particle is defined as the smallest form of matter, incapable of being divided into simpler substances. For centuries, humanity believed that atoms were the ultimate building elements of everything. But as physics progressed, we realized that even atoms are composed of more basic constituents, ones that not only create all matter, but also help decode the forces shaping the cosmos. The journey begins with the atom's discovery. In the early 1800s, John Dalton introduced the idea that all matter is formed from indivisible units, which he termed atoms. However, it wasn't long before researchers found that atoms themselves weren't indivisible. In the early 1900s, groundbreaking work by scientists like J.J. Thomson, Ernest Rutherford, and Niels Bohr showed that atoms have a central core, the nucleus, made of protons and neutrons, with electrons orbiting around it. This revelation paved the way for a deeper investigation into what lies even further beneath. With technological advancements, especially the invention of particle accelerators, scientists were able to delve into even more obscure constituents of matter. Through experimental breakthroughs, it became evident that protons, neutrons, and electrons were not the final layer. Instead, these were made up of even smaller units. This gave rise to what we now call the Standard Model of particle physics, a framework that classifies the elementary particles that constitute everything in the universe and explains the interactions between them. The Standard Model groups these basic particles into two primary categories: fermions and bosons. Fermions are the matter makers, while bosons are responsible for the forces acting between particles. Let's explore these classifications further. Fermions obey what is called the Pauli exclusion principle, which dictates that no two identical fermions can exist in the same quantum state at the same time. These include quarks and leptons, the building blocks of all physical matter. There are 6 varieties of quarks: up, down, charm, strange, top, and bottom. Similarly, there are 6 leptons: electron, muon, tau, and their corresponding neutrinos. Quarks never appear alone in nature. They always group together to form larger particles, such as protons and neutrons. On the other hand, electrons are solitary, stable particles that orbit around atomic nuclei and play a key role in chemical bonding. Quarks are bound together by the strong nuclear force, which is carried by a particle known as the gluon. This force is immensely strong at small distances, effectively confining quarks inside protons and neutrons. Gluons themselves have no mass, but possess a property known as color charge, which governs quark interactions. Although it shares a name with color, this charge is not related to actual color. It's a unique aspect of the strong force. Leptons, unlike quarks, are unaffected by the strong nuclear force. Instead, they interact via the electromagnetic force and the weak nuclear force. For example, electrons respond to the electromagnetic force, responsible for electricity and magnetism, while neutrinos are only influenced by the weak force, which plays a key role in radioactive decay. Though neutrinos are incredibly difficult to detect, they are among the most numerous particles in the cosmos. Now, let's look at bosons, the carriers of nature's fundamental forces. While fermions make up the stuff of the universe, bosons facilitate the forces between them. There are 4 basic forces in nature: gravity, electromagnetism, strong nuclear, and weak nuclear forces. Each of these is mediated by different bosons. The photon carries the electromagnetic force. The W and Z bosons handle the weak force, crucial for certain nuclear reactions. The gluon, as mentioned earlier, governs the strong force. Then there's the Higgs boson, discovered in 2012, associated with the Higgs field. This field is vital because it imparts mass to particles. According to the Higgs mechanism, particles acquire mass by interacting with this field. The stronger the interaction, the heavier the particle. The discovery of the Higgs boson at CERN was a historic moment, confirming a missing piece of the Standard Model. But despite its elegance and success, the Standard Model has limitations. For one, it doesn't account for gravity, which is best explained by Einstein's general theory of relativity. It also offers no explanation for dark matter and dark energy, unseen substances and forces that dominate the universe's composition. Moreover, many values within the Standard Model, like particle masses, seem arbitrary and lack deeper theoretical justification. This is where the search for new physics begins, the next frontier in particle science. Physicists are exploring ideas to extend our current understanding of the universe. One major contender is string theory. It proposes that all particles are not point-like, but instead are tiny, vibrating strings. Different vibration patterns create different particles. If proven true, string theory could unify all four fundamental forces, including gravity, into a single, elegant framework. Another hot topic of research is neutrinos. These enigmatic particles have tiny masses and interact only weakly with other matter. Yet, they hold deep secrets about the universe. Trillions of neutrinos pass through our bodies every second, unnoticed. Unraveling their nature could reshape our understanding of the cosmos. A further mystery lies in dark matter. While we can't see it directly, we know it exists due to its gravitational pull on visible matter. It's estimated to make up about 27% of the universe's total content. Some theorists believe it may be made of unknown particles like WIMPs, weakly interacting massive particles. Finding such particles could transform our view of reality. As we push forward in particle physics, our assumptions about space, time, and existence are being tested. The more we uncover about the universe's tiniest components, the more we realize how much remains unknown. Are there still undetected particles out there? Could there be unknown forces at play? Searching for these answers is among the most thrilling and meaningful pursuits in science today. Ultimately, studying elementary particles isn't just about identifying matter's ingredients, it's about understanding the universe itself. By peeling back the layers of the smallest known elements, we get closer to unveiling the profound nature of reality, the mechanisms that shape our world, and the origin of everything. This quest continues, and with every new breakthrough, we edge closer to unlocking the most profound secrets of existence. The quantum fabric of reality pictures standing alone in a vast, open expanse, seemingly still and empty. The earth beneath your feet feels stable, but within the quantum realm, this emptiness is anything but lifeless. It's teeming with invisible, ceaseless motion. What you're experiencing is not a regular field, but a quantum field, a foundational idea in one of modern physics' most advanced models. Quantum field theory (QFT). Initially, it defies everyday logic to imagine vacant space as energetic, but QFT reveals that what looks like a void is actually alive with unceasing activity, particles continually appearing, vanishing, and influencing one another. In our normal experience, we visualize particles as tiny, solid items, like marbles rolling in a tray. But QFT turns that on its head. In this framework, particles aren't independent structures at all. They are visible expressions of deeper, omnipresent quantum fields that stretch across the cosmos. These fields, not the particles, are the actual building blocks of everything. Electrons, photons, quarks, and other particles are simply energy pulses or vibrations within these ever-present fields. Let's rewind and unpack this principle. Imagine a calm pond. Drop a pebble into the water, and you'll see ripples spreading outward. In a similar fashion, particles such as electrons are just wave-like disruptions traveling through the quantum fields that fill space. Just like the pond remains even as waves ripple through it, the quantum field continues to exist even when a particle appears to move. But unlike pond waves, these quantum waves follow the strange, probabilistic rules of quantum mechanics, not the predictable laws of classical physics. Each kind of fundamental particle corresponds to a distinct quantum field. For instance, electrons are disturbances in the electron field. Photons are tremors in the electromagnetic field. Importantly, these fields don't exist at specific coordinates. They span all of space, uninterrupted. What we identify as particles are just localized effects of these extended fields. Though particles seem like separate units, they are inseparable from the field they emerge from. They are its energetic ripples. One of the profound implications of this is that quantum fields are the basis for all interactions in the universe. In classical physics, forces like gravity or electromagnetism act through carrier particles, gravitons and photons, respectively. In QFT, these interactions arise through the exchange of virtual particles, short-lived fluctuations that briefly emerge to facilitate force transmission. Take the example of two electrons repelling each other. According to QFT, this repulsion is made possible by the passing of virtual photons, particles that emerge momentarily to convey electromagnetic force. Though you can't detect them directly, these virtual messengers are fundamental to the working of quantum forces. Let's explore this further. Visualize a crowded city intersection, people constantly moving, brushing past, briefly connecting. These momentary exchanges mirror the behavior of virtual particles in the quantum realm. They are constantly flashing in and out of being, mediating interactions between real particles. Despite their transience, they obey energy conservation because their appearance is so brief. These tiny blips explain how fundamental forces act across space. The idea of virtual particles also helps us grasp vacuum fluctuations. Even in total vacuum, where no real particles are detectable, the fields don't sit idle. They pulse, generating temporary energy surges that spawn particle-antiparticle pairs. These ephemeral twins arise from nothing, last for a heartbeat, then cancel each other out, restoring the energy to the field. This process is called vacuum polarization. It may sound like it contradicts energy conservation, but it actually aligns perfectly with Heisenberg's uncertainty principle, which allows short-term borrowing of energy as long as it's swiftly paid back. In this sense, even nothing is full of something, namely, flickers of unseen energy. These vacuum dynamics aren't just theoretical. They've been validated through experiments like the Casimir effect, where two uncharged metal plates placed close together in a vacuum feel a pull due to field fluctuations between them. This surprising force confirms that even the quietest vacuum is brimming with invisible activity. QFT isn't limited to describing everyday particles like electrons and quarks. It also governs the carriers of fundamental forces. Photons mediate electromagnetic force, gluons control the strong nuclear force, and the weak nuclear force is regulated by W and Z bosons. While gravity isn't yet fully merged with QFT, it's hypothesized to operate through gravitons, another form of quantum exchange. What sets QFT apart is its unification of two cornerstones of modern physics: quantum mechanics, which rules over atomic scale behavior, and special relativity, which governs motion near light speed. These two frameworks long resisted integration until QFT brought them together. In QFT, particles are excitations in relativistically consistent fields, meaning the theory holds true even at velocities close to light speed. This union of quantum uncertainty and relativistic motion is one of QFT's greatest achievements. Perhaps its most celebrated success is the Standard Model of particle physics. This theory describes the electromagnetic, weak, and strong nuclear forces and has passed countless experimental tests, including those at CERN's Large Hadron Collider. Within this model, all matter particles like quarks and electrons are just quantum field ripples, while all forces result from exchanging virtual particles. The discovery of the Higgs boson, which imparts mass to other particles, was a landmark confirmation of QFT. Despite this, QFT is not the final word. A major unsolved puzzle is gravity. It remains outside the established QFT framework. Integrating gravity with QFT is one of physics' greatest quests. Theories like string theory and loop quantum gravity attempt to solve this, but a unified theory is still elusive. QFT also opens profound questions about the nature of space and existence. If all of space is woven with quantum fields, and particles are just their ripples, then is space truly empty? Or is it a vibrant arena of ceaseless fluctuations we barely perceive? These mysteries continue to challenge our understanding and push the boundaries of science. In summary, quantum field theory has radically changed how we perceive the universe. By revealing that particles are not distinct units, but vibrations in underlying fields, it offers a deeper, more elegant view of reality. From describing forces to understanding the quantum vacuum, QFT has given us extraordinary insights. And while the journey to unite all forces, especially gravity, is still underway, QFT remains one of the most groundbreaking and successful scientific theories of all time. The warped reality of space and time. Visualize standing alone upon a limitless, barren surface, a flat and unbroken stretch of land extending endlessly in every direction. Above, the sun hovers high in the sky, radiating warmth and brightness evenly across the ground. Now imagine someone arrives, placing an enormous stone in the center of this vast terrain. As this massive object settles in place, the surface around it subtly begins to dip and deform. What was once a perfectly flat area now appears gently bowed, resembling a stretched-out trampoline sinking beneath the weight. This bending of the ground offers a metaphor for how space and time behave around heavy objects, as explained in Albert Einstein's groundbreaking concept, the theory of general relativity. This theory revolutionized the way we view the universe by offering a radically new explanation for gravity and reshaping how we perceive space and time. Before Einstein introduced his theory, our understanding of gravity came from Isaac Newton. Newton described gravity as an invisible force that acted instantly between two masses, pulling them together, much like a magnet attracting metal. Under this view, if you held an apple above the earth and let go, gravity would immediately draw it downward. Newton's model was excellent for explaining slow-moving objects in everyday life, but it faltered when applied to celestial bodies traveling at or near the speed of light. That's where Einstein's radical insight changed everything. Rather than treating gravity as a pulling force between objects, he proposed that massive objects bend the very structure of space and time, collectively known as spacetime. According to Einstein, mass and energy deform the fabric of spacetime itself, and this warping determines how objects move through it. To illustrate this, imagine spacetime as a stretchable sheet or net. When something heavy, like a star or planet, rests on it, the fabric dips. Any smaller object nearby, like a planet or a beam of light, travels along these curves, not because it's being pulled, but because spacetime itself is shaped in a way that guides its path. Einstein famously likened this to a trampoline. Place a heavy ball in the center, and the surface sags. Then roll a smaller marble near it. The marble will spiral inward, following the curve. That's how gravity works in this new view. It's the motion of objects responding to the warping of spacetime caused by mass and energy. One of the most remarkable predictions made by general relativity is that extremely massive bodies, such as the Sun, can bend light itself. This phenomenon is known as gravitational lensing. Imagine a beam of light traveling toward Earth from a distant star. As it passes near the sun's mass curves the spacetime around it, causing the light to arc ever so slightly. To observers on Earth, the star appears to be in a slightly different position than it actually is. Astronomers have repeatedly confirmed this effect using both Earth-based telescopes and instruments in space, offering strong proof that Einstein's theory is accurate. But the implications go even further. General relativity shows that gravity can distort time itself, warp the shape of space, and even influence the path of light. One of the most extreme and awe-inspiring consequences of this theory is the black hole, a region of space where gravity is so intense that not even light can escape. Black holes are formed when massive stars exhaust their fuel and collapse under their own weight. According to general relativity, this collapse creates a singularity, a point where spacetime curves infinitely and the gravitational pull becomes immeasurably strong. Around this singularity lies the event horizon, a boundary beyond which nothing, not even light, can escape. It's the ultimate point of no return. As light approaches a black hole, it's bent so severely that it creates a glowing ring surrounding the dark center. In 2019, scientists unveiled the first direct image of a black hole located in the galaxy M87. The photo revealed a dark central region, the shadow of the black hole, surrounded by a bright ring of distorted light. This matched Einstein's predictions perfectly, and it marked a historic confirmation of a theory conceived over a century ago. Another essential idea within general relativity is that spacetime is not a static backdrop. It is an interconnected, dynamic entity combining both space and time into one seamless four-dimensional continuum. What's more, time itself is not fixed. It flows differently depending on how fast you move and how close you are to a strong gravitational field. For instance, if you were to board a spaceship and accelerate to speeds close to that of light, time would slow down for you relative to someone who remains on Earth. This is known as time dilation, and it has been confirmed with remarkable precision. Experiments involving particle accelerators and atomic clocks aboard fast-moving aircraft have all demonstrated that time passes differently in high-speed or high-gravity conditions. One particularly fascinating consequence of time dilation is that time can tick at slightly different rates depending on your position. For example, a person aboard a satellite orbiting Earth would experience time at a marginally faster rate than someone on the planet's surface. This isn't just theoretical, it's a critical correction built into the GPS navigation system. Without accounting for time dilation, GPS would quickly drift out of sync and deliver inaccurate locations. General relativity has also enabled us to detect some of the universe's most dramatic events through gravitational waves, subtle ripples in spacetime generated by titanic cosmic collisions, such as the merger of black holes or neutron stars. These waves were predicted by Einstein long before we had the technology to find them. In 2015, scientists finally recorded the first gravitational wave, opening up a completely new way to observe violent astronomical phenomena. These waves carry information about the origin and nature of their source, allowing scientists to study cataclysmic events billions of light-years away. Through gravitational waves, we gain insight into not just black holes, but also the very expansion of the universe and the fabric of reality itself. In the end, Einstein's theory of general relativity didn't merely revise Newton's view of gravity, it transformed our entire picture of the cosmos. Space, time, and gravity are no longer seen as separate and rigid forces. Instead, they are intricately connected, ever-changing features of a living universe. Spacetime can stretch, bend, twist, and vibrate in response to the energy and mass within it. From light-bending black holes to time-warping satellite systems and spacetime-shaking gravitational waves, general relativity reshaped our understanding at the most fundamental level. It urges us to reconsider what we mean by space, time, and reality of the science behind black holes. Imagine a location in the cosmos where the fundamental principles that govern reality cease to function, where the fundamental forces converge so powerfully that they unravel. At the heart of each black hole resides an enigmatic point called a singularity, where gravitational force becomes so overwhelming that it twists and collapses the very structure of space and time. This is the birthplace of black hole science, a branch of physics that challenges our understanding of the cosmos at its most extreme limits. The theoretical roots of black holes stretch back to the 1700s, but it was Albert Einstein's formulation of the general theory of relativity in the early 1900s that began to illuminate how such bizarre celestial phenomena could arise and operate. According to this theory, a sufficiently massive body undergoing gravitational collapse can form a black hole, a space region with such powerful gravity that even light cannot break free. Once anything crosses the event horizon, the boundary beyond which escape is impossible. It is lost forever. The study of black holes is far from straightforward, but gaining insight into them is vital to deepening our grasp of the universe. These regions are where the limits of spacetime are pushed to their maximum, serving as experimental grounds for theories about gravity, quantum behavior, and thermodynamics. In fact, black holes are among the most promising areas to explore the frontiers of modern physics. A crucial principle in comprehending black holes lies in the concept of escape velocity. Everything in existence exerts gravitational attraction, pulling other objects toward it. Ordinarily, this force is mild, and we barely notice it in daily life. However, when an object possesses immense mass, the gravitational pull becomes significantly more potent. The escape velocity refers to the speed required to break free from this gravitational influence. For most celestial bodies, this speed is manageable, but as mass compacts further, the necessary speed increases. In the case of black holes, the required velocity exceeds the speed of light, rendering them invisible, as not even light can emerge from their grip. Rather than emitting or reflecting light, black holes are detected through their interactions with surrounding material. The event horizon forms the critical border around a black hole. Once crossed, nothing returns. If you fell into a black hole, you would pass through this boundary and be irresistibly drawn toward the singularity. Time itself would seem to decelerate due to the extreme spacetime distortion, and from an outside viewer's point of view, you'd appear frozen at the edge of the event horizon. This leads to one of the strangest phenomena associated with black holes, the time paradox. As you approach a black hole, the gravity intensifies, causing an effect known as gravitational time dilation. From your own viewpoint, time proceeds normally. But to a distant observer, your movement appears to slow dramatically, eventually seeming to halt near the horizon. At the core of the black hole lies the singularity, a location of infinite gravitational intensity and infinite spacetime curvature. Here, the physical laws we rely on disintegrate entirely, and no existing scientific theory can accurately describe the conditions. What truly unfolds within the singularity remains a profound mystery. Nonetheless, black holes offer indirect paths for exploration. While the inside is inaccessible, we can study the behavior of material drawn toward them. Gas and dust pulled in often form a swirling accretion disk around the black hole. As matter spirals inward, it heats to extraordinary temperatures and emits intense radiation, especially in X-ray wavelengths. This emission enables scientists to detect black holes across vast cosmic distances. Interestingly, black holes don't simply gobble everything up like cosmic vacuum cleaners. On the contrary, many of them are believed to influence the formation of galaxies and large-scale cosmic structures. As matter falls inward, the energy released can shape the environment. For instance, the supermassive black hole at the center of the Milky Way likely drives some of the universe's most powerful phenomena, like quasars, which are brilliant and remote entities emitting immense radiation. Black holes also open a window into one of physics' greatest conundrums: how to unify general relativity with quantum theory. While general relativity governs massive bodies and the warping of spacetime, quantum mechanics explains how particles behave at the smallest scales. Though each framework works well independently, they clash under the extreme conditions present in a singularity where both gravity and quantum forces dominate. Decoding black holes may eventually lead to a long-sought quantum theory of gravity, one of the ultimate goals of contemporary science. One of the most transformative breakthroughs in black hole research came in 1974 from physicist Stephen Hawking. He revealed a connection between black holes and thermodynamics by proposing that black holes aren't completely dark, but instead emit radiation, now called Hawking radiation. Quantum mechanics suggests that even empty space teems with fleeting particle pairs. Near the event horizon, one of these particles may fall in while the other escapes. The escaping particle appears as radiation, gradually draining the black hole's mass and energy. Over time, this could cause the black hole to evaporate, though this process would take unimaginably long timescales. Hawking's insight reshaped our understanding of black holes, revealing that they could have finite lifespans. This idea also sparked a profound question. If a black hole completely vanishes, what becomes of the information it once held? This is known as the black hole information paradox, one of the most hotly debated dilemmas in theoretical physics. Solving it could reshape our comprehension of quantum mechanics and the very nature of reality. Despite the strides we've made, black holes continue to hold countless secrets. We still lack a full understanding of what lies at the singularity or how to harmonize quantum principles with relativistic physics in these conditions. What is certain, however, is that black holes are among the most compelling and mysterious entities in existence. They defy our core assumptions about the universe and will undoubtedly remain central to pushing the limits of scientific discovery for generations to come. Einstein's game-changing theory. Unveiling special relativity. Imagine you're sitting on a moving train, gazing out the window as the landscape zips past. Everything inside feels perfectly smooth, the motion of the train beneath you is steady, and all seems physically normal. The principles of physics appear to operate just as expected. But now, consider this. An observer standing on the ground, watching the train speed by, sees a very different picture. To them, you are zooming past at a high velocity. Yet from your perspective inside the train, it feels like you're stationary and everything is functioning normally. This fascinating contrast in perception based on different viewpoints, also known as frames of reference, is the foundation of Albert Einstein's groundbreaking concept, the theory of special relativity. A radical shift in understanding space and time. Special relativity, one of the most pivotal discoveries in modern physics, completely reshaped our comprehension of space and time. At its core, the theory asserts that the laws of physics remain consistent for all non-accelerating observers, no matter how fast they're moving. Although that premise sounds straightforward, the consequences are anything but simple. The theory reveals that space and time are not rigid, fixed quantities. Instead, they are interlinked and elastic, capable of bending and reshaping in response to motion, especially motion at extreme speeds. The invariable speed of light. A central revelation of special relativity is this: the speed of light is always constant, no matter how fast the observer or light source is moving. This goes against our usual intuition. Suppose you're aboard a spaceship cruising through the cosmos and you shine a flashlight forward. Meanwhile, someone else in a spacecraft moving in the opposite direction might expect your light beam to retreat from them at a speed faster than light. But Einstein's theory says otherwise. Whether you're racing toward each other or drifting apart, both of you will measure the beam's speed as exactly 186,282 miles per second, or roughly 300,000 kilometers. This fixed speed of light is the bedrock of special relativity, and it gives rise to some of its most astonishing effects. Bending reality. Time and space are fluid. To dive deeper, we need to accept that space and time aren't standalone concepts. According to Einstein, they're components of a larger, combined entity called spacetime. Think of spacetime as a universal fabric that stretches across the cosmos. When a massive object moves through it, it distorts the fabric, much like a heavy ball on a trampoline. The faster it moves, the more it distorts spacetime. This is when the truly strange things begin to happen. As you approach the speed of light, time slows down for you relative to someone standing still. At the same time, the space in your direction of travel contracts. These effects are known as time dilation and length contraction, two of the most important and bizarre outcomes of special relativity. Time dilation. Time ticks differently. Let's begin with time dilation. If you're flying through space in a spaceship nearing the speed of light, time flows more slowly for you than for someone remaining stationary on Earth. This isn't just theory. It's been proven with high-precision atomic clocks placed on fast-moving jets and satellites. Imagine an astronaut traveling at near light speed for a few years. Upon returning to Earth, they might discover that decades have passed for those back home, even though only a few years passed for them. The closer you get to light speed, the more pronounced this time slowdown becomes, until, in theory, time would freeze altogether at light speed. This defies everyday logic because we're used to time ticking at a consistent pace. But in Einstein's universe, time is not absolute. It depends entirely on your speed. It can stretch or compress depending on how fast you're moving. Yet, this doesn't mean time is objectively slower or faster. It simply means that observers moving at different velocities experience time differently. Length contraction. Distances shrink with speed. Now, let's talk about the second major effect, length contraction. Just as time slows down, the length of objects in the direction of motion gets shorter as you approach the speed of light. For instance, from the viewpoint of someone outside your speeding spaceship, the ship's length would shrink even though its width and height remain the same. Importantly, this isn't a visual illusion, it's a genuine physical phenomenon. The theory of special relativity predicts that space itself reshapes depending on your speed. Rethinking reality. A new view of space and time. How can such mind-bending ideas be possible? After all, our senses tell us that time flows steadily and distances remain fixed. That's because we've long followed Newton's model, where space and time are constant and universal, unaffected by motion. But in Einstein's relativistic model, space and time form a four-dimensional spacetime fabric that twists and flexes based on an object's speed. This connected nature of space and time results in time dilation and length contraction, not because anything is wrong, but because reality itself is more relative than we imagined. The faster you move, the more spacetime deforms around you. Real-world proof. Evidence of relativity. This revolutionary concept isn't just a theory on paper, it's been confirmed through many real-world experiments. Take muons, for example, tiny particles formed when cosmic rays strike Earth's atmosphere. These muons move so fast that their internal clocks slow down compared to observers on Earth. As a result, they survive longer and travel farther than they would if they were at rest. This extended lifespan has been observed and measured, serving as direct evidence of time dilation, one of special relativity's core predictions. The cosmic speed limit. Why nothing beats light. Perhaps the most startling implication of special relativity is that no object can move faster than light. According to Einstein, as you accelerate closer to light speed, the amount of energy required grows astronomically. To reach light speed, you'd need infinite energy, which is physically impossible. So, light speed becomes a cosmic speed limit, one that nothing can break. This has huge implications for space travel, communication, and how we understand cause and effect. It means that no signal or object can transmit information faster than light, setting clear boundaries on how far and how fast we can reach across the universe. Relativity, transforming modern physics. Even though special relativity introduces concepts that seem alien to our senses, it has been rigorously tested and proven. It now stands as one of the most dependable theories in all of science, forming the base of general relativity and even modern technologies like GPS, which must correct for relativistic effects to remain accurate. Still, the implications of the theory remain deeply non-intuitive, forcing us to revisit our understanding of motion, time, and space. Its most dramatic effects are seen at speeds far beyond our daily experience. But even in our everyday world, the influence of special relativity subtly shapes the universe and continues to inspire the cutting edge of physics. The observer influence in quantum reality. Let's begin by examining a common example. Imagine you want to check the temperature of a cup of coffee. You use a thermometer, immerse it in the coffee, and read the temperature. During this action, the thermometer simply registers the coffee's temperature without significantly affecting it. One might assume this is how all measurements operate, collecting data without altering the subject. But in the quantum domain, the scenario is far more complex. The very act of measuring can disturb the system under scrutiny in profound ways. Central to the observer influence is the principle of superposition in quantum theory. Particles do not possess definite attributes until they are measured. Instead, they exist as a superposition, a combination of all possible states. Consider an electron orbiting within an atom. Unlike classical physics, where it follows a clear path, the electron exists in a probabilistic cloud, potentially present in multiple places simultaneously with varying speeds, spins, and energy levels. It is only upon measuring its position or momentum that this cloud collapses into one definitive outcome. Hence, the observer influence implies that it is not only our knowledge of a system that changes upon measurement, but the system itself alters. The most renowned demonstration of the observer influence is the double-slit experiment, a foundational experiment in quantum physics. Imagine a barrier with two slits and a screen behind it that detects where particles, such as electrons, land. When electrons are fired at the slits without measuring which slit each passes through, they behave like waves, creating an interference pattern on the screen, as if each electron passes through both slits simultaneously and interferes with itself. However, if a detector is placed to observe which slit the electron travels through, the interference pattern vanishes, and the electrons behave like particles again, landing in distinct locations. Here, the simple act of measuring or observing the electron's path causes a dramatic change in its behavior. This phenomenon brings us to a deeper philosophical question. If observation alters a particle's behavior, what implications does that have for the nature of reality itself? Some physicists and philosophers argue that the universe does not possess fixed properties until it is observed. This idea departs radically from everyday experience, where objects such as cars or trees appear to exist independently of whether anyone looks at them. In the quantum realm, particles seem to exist in a state of possibility, an ensemble of probabilities, until observed. Thus, the observer influence challenges our conventional understanding of reality. Is the universe merely a collection of potentialities waiting to be realized through conscious observation? A famous quote related to this effect comes from physicist Niels Bohr, who stated that everything we call real is made of things that cannot be regarded as real in the classical sense. Bohr emphasized the strange probabilistic nature of quantum reality, contrasting with our intuition that objects always have definite properties. For example, an apple is always red, a chair always has four legs. Quantum mechanics, however, reveals that on the subatomic scale, reality is far more fluid and uncertain. What does this mean in practical terms? If observation can change a system's state, what role does the observer play in the universe? One intriguing theory proposed by physicist John Archibald Wheeler is the idea of the participatory universe. Wheeler suggested that the universe itself depends, in some way, on the observer. He viewed the universe not as a static, pre-existing entity, but as something actively brought into existence through the act of observation. This does not imply the universe ceases to exist when unobserved, but suggests its properties might be influenced by our perception. Wheeler's participatory universe concept connects closely with the idea that consciousness holds a fundamental role in shaping reality. Though still controversial, this notion has attracted attention in both physics and philosophy, especially in discussions about quantum mechanics and consciousness. Some theorists propose that consciousness is not just a passive witness, but a co-creator of the quantum world we experience. Of course, not all scientists agree with this interpretation. Many argue that the observer influence simply reflects the limitations of measurement instruments. From this perspective, the effect does not mean consciousness affects particles, but that any measurement interaction inevitably disturbs quantum systems. For instance, in the double-slit experiment, placing a detector at the slit's triggers changed not because of human awareness, but due to the physical interaction between the measuring device and the particles. Thus, the observer effect may be less about consciousness and more about the unavoidable disturbance caused by measurement. While these debates continue, the observer influence profoundly impacts our understanding of the quantum realm and reality itself. It reveals that at the tiniest scales, the boundary between observer and observed becomes blurred, challenging fundamental assumptions about the separation between subject and object, between perceiver and perceived. There are also practical consequences. One of the most promising areas born from quantum mechanics is quantum computing. Quantum computers harness principles like superposition and entanglement to perform calculations far beyond classical capabilities. Yet, the observer influence is crucial here. To extract meaningful information, quantum systems must be measured, which inevitably disturbs their state by collapsing superpositions into definite outcomes. This challenge requires managing quantum states carefully and minimizing measurement disturbances. Quantum cryptography also relies on quantum principles, including the observer effect. Its security depends on the fact that any attempt to intercept quantum information disturbs its state, alerting legitimate users to the intrusion. In this way, the observer influence becomes a beneficial feature, providing security levels unattainable by classical encryption. Therefore, the observer influence is not merely a philosophical curiosity, but has tangible real-world effects, shaping everything from quantum computer design to secure communication technologies. It challenges our conception of the universe and highlights the deep interconnection between observer and observed. Whether exploring consciousness, reality's fabric, or technological frontiers, the observer influence reminds us that the universe is far stranger than it appears. In the quantum domain, nothing is ever as straightforward as it seems. Even our simplest observations can alter the very fabric of reality itself. Unveiling gravitational waves. Imagine you're beside a serene lake. The surface is so calm and clear that it mirrors the sky above. Suddenly, someone tosses a pebble into the still water, and gentle waves begin to ripple outward, distorting the reflection. Now, replace the pebble with a monumental event, such as the collision of two black holes or the explosion of a dying star. Instead of water, picture the ripples moving through the very structure of space and time. These cosmic ripples are what we call gravitational waves. Gravitational waves stand among the most astonishing and significant concepts predicted by Albert Einstein's groundbreaking theory of general relativity. They offer a revolutionary way of observing the universe. At their core, gravitational waves are oscillations in the space-time continuum that arise when colossal objects undergo acceleration, warping the geometry of the universe itself. These waves, traveling at the speed of light, carry with them invaluable clues about some of the most energetic and turbulent occurrences in the cosmos. For many years, the idea of gravitational waves remained purely theoretical. Though Einstein introduced the concept in his theory over a century ago, no one had been able to observe them directly. It wasn't until recent decades that scientific advancements enabled researchers to capture these elusive signals. When the first detection finally happened, it wasn't merely a scientific success. It was a paradigm-shifting moment that opened a new observational gateway into the universe. To understand how gravitational waves function, let's revisit the fundamentals of general relativity. In Einstein's view, space and time are not separate components, but together form a unified, four-dimensional entity known as spacetime. Massive bodies, such as stars, planets, and black holes, curve this fabric, much like a heavy object pressing down on a taut rubber sheet. This curvature is what we recognize as gravity. Now, when massive entities like orbiting black holes or neutron stars interact, they disturb this space-time fabric, sending out ripples that extend far and wide. Much like the waves in our earlier pond analogy, these gravitational ripples cause space-time to stretch and compress as they pass. Upon reaching Earth, they induce incredibly minute shifts in the distances between physical objects, changes that are so subtle they can only be captured using highly sensitive instruments. Even with our most advanced technology, detecting gravitational waves is an extraordinary challenge. Only violent astrophysical events, such as the fusion of two massive black holes or the union of neutron stars, produce waves strong enough to be identified. Einstein suspected these waves would be so faint that we might never perceive them, and for nearly a century, they remained hidden from our grasp. That all changed in 2015. Scientists working with the Laser Interferometer Gravitational Wave Observatory LIGO announced a historic breakthrough. They had, for the first time, recorded the presence of gravitational waves. These waves originated from a colossal black hole collision occurring approximately 1.3 billion light-years from Earth. LIGO's cutting-edge detectors, which utilize the technique of laser interferometry, picked up the unmistakable signal. Space-time itself was trembling from one of the most dramatic cosmic events imaginable. This discovery not only confirmed a core tenet of Einstein's theory, but also inaugurated a new era of astrophysics. But what precisely occurs during such a gravitational wave event? When two compact, incredibly dense objects, such as black holes, begin spiraling toward each other, they generate waves in spacetime. As their orbit tightens and they near collision, the waves intensify, akin to how water splashes more vigorously as a stone sinks deeper. The actual merger emits a burst of energy that ripples through space, embedding information about the black hole's masses, spin, and the dynamics of the crash. Despite the immense power of these phenomena, the waves themselves diminish greatly as they traverse space. By the time they arrive at Earth, the variations they cause are extraordinarily subtle, changes on the scale of 1,000th the diameter of a proton. LIGO's detectors operate by splitting a laser beam along two perpendicular paths and analyzing how those paths alter when a gravitational wave passes, slightly stretching or compressing spacetime. This level of precision is nothing short of breathtaking. The signal LIGO captured in 2015 lasted mere milliseconds, but it carried a trove of data. That fleeting moment helped unlock secrets of the universe that had remained inaccessible for eons. The achievement marked not just a scientific milestone, but also a tribute to the dedication of thousands of engineers and researchers over decades. Gravitational waves offer more than just insights into black holes. They allow us to peer into the early epochs of the universe, potentially uncovering details about the birth of stars and galaxies. By studying these cosmic oscillations, scientists can better understand extreme environments such as neutron star interiors and the forces involved in black hole mergers. What makes gravitational waves so uniquely valuable is their ability to convey information unreachable by other forms of observation. Light, whether it be visible, infrared, or ultraviolet, can be blocked or warped by cosmic dust and gas. Gravitational waves, however, pass through all matter undeterred. This makes them an unparalleled tool for astronomers, unveiling corners of the universe that were once thought to be forever concealed. The groundbreaking detection in 2015 heralded the dawn of gravitational wave astronomy. Since then, LIGO, along with its European counterpart Virgo, has identified numerous additional wave signals, including those from neutron star collisions. These detections have reshaped our cosmic perspective and promise even more revelations as the science evolves. However, the path to detecting gravitational waves is fraught with technical hurdles. The distortions in spacetime caused by these waves are minuscule, demanding instruments of exceptional sensitivity. LIGO, for example, is built to identify movements as tiny as 1,000th of a proton's width. Achieving this necessitates extraordinary engineering, from advanced vibration isolation to sophisticated noise cancellation systems that shield measurements from environmental disturbances like earthquakes, vehicular traffic, and even air particle motion. Despite the complexity, the advent of gravitational wave detection has fundamentally transformed our grasp of the universe. It has equipped us with an unprecedented observational tool, enabling us to witness phenomena like black hole mergers and neutron star collisions. Each signal enriches our understanding of gravity, space, and time. The realization of gravitational waves underscores the dynamism and mystery of the cosmos. It speaks to the power of human curiosity, perseverance, and the relentless drive to understand the unknown. As our exploration of these ripples continues, they will surely reveal truths long hidden, truths embedded in the very fabric of the universe, waiting for the waves of creation to whisper them into discovery. The mysterious boundary of no return, the boundary known as a black hole's event horizon, is one of the most fascinating and mysterious phenomena in the cosmos. It represents the ultimate limit, the region beyond which absolutely nothing can break free from the immense pull of gravity, not even light. Although this boundary plays a crucial role in our comprehension of black holes and the fundamental nature of space and time, the event horizon remains a puzzling and difficult to grasp idea. It stretches our understanding and calls for a closer examination of the very structure of the universe. At its essence, the event horizon isn't a solid surface like a planet's crust or a star's exterior. Instead, it's a boundary in the continuum of space and time, a point beyond which any chance of escaping a black hole vanishes entirely. This limit is closely tied to the black hole's unique characteristics. What sets the event horizon apart is that the required speed to escape it exceeds that of light itself, roughly 300,000 kilometers per second. This means that once anything, including light, goes beyond this invisible perimeter, it is inevitably drawn into the core of the black hole, the singularity, where the curvature of space-time becomes infinite. To understand this strange region more deeply, let's dissect the principles at play. Gravity, the force that governs the motion of all objects in space, becomes extreme in a black hole's surroundings. In fact, a black hole forms when a star of considerable mass collapses under the weight of its own gravity. This catastrophic collapse compresses the star's core into a point of infinite density, and the gravity in that area grows so powerful that it warps the structure of space and time itself. The event horizon marks the threshold at which this gravitational force becomes so overpowering that nothing, no matter or signal, can break away once it crosses the limit. A useful analogy is that of a waterfall's edge. Imagine yourself standing near the brink of a huge waterfall. As you move closer, you feel the current pulling you forward. At that moment, you still have the power to turn back. But once you step over the edge, the force of gravity takes over completely, dragging you down, and there's no returning. The event horizon works in the same way. Crossing it seals your fate, and nothing, not even light, can escape its grasp. What makes the event horizon even more complex is its deep relationship with time and space. According to Einstein's general theory of relativity, massive objects distort the fabric of space-time, and the greater their mass, the more they bend this fabric. Black holes, being incredibly dense and compact, stretch space-time to such an extreme that the usual rules of physics seem to collapse. The event horizon defines the boundary where this distortion becomes so severe that our standard understanding of time, space, and physics itself no longer applies. One of the most astonishing aspects of the event horizon is how it alters time. From the point of view of a distant observer, time appears to slow dramatically for any object approaching the event horizon. As the object nears the threshold, it seems to slow down more and more, ultimately appearing frozen just outside the boundary. However, from the falling object's own perspective, it crosses the event horizon smoothly, without any noticeable shift in its experience of time. This strange difference arises from the distorted structure of space-time near a black hole. It's essential to realize that the event horizon isn't a rigid or unchanging edge. Its size depends entirely on the mass of the black hole in question. A larger black hole will have a wider event horizon, while a smaller one will have a more compact boundary. This distance is known as the Schwarzschild radius, named after physicist Carl Schwarzschild, who first solved the equations of general relativity describing black holes. The Schwarzschild radius is directly tied to the mass of the black hole and represents the point where the escape speed surpasses the speed of light. This paradox arises from a conflict between two major theories, quantum mechanics and general relativity. Quantum theory insists that information can never be entirely destroyed. Yet, when something falls past the event horizon, it appears that all information about it vanishes, leading to a contradiction. This dilemma has fueled intense debate among scientists for decades. One idea that attempts to solve the issue involves information scrambling, which proposes that while information isn't destroyed, it becomes highly mixed and encoded within the quantum structure of the black hole, possibly still retrievable in some form. The event horizon isn't just a theoretical construct. In 2019, the Event Horizon Telescope HT collaboration achieved a groundbreaking milestone by capturing the first image of a black hole's event horizon. By using an array of radio telescopes across the globe, scientists observed the supermassive black hole at the heart of the M87 galaxy. The photograph showed a luminous ring encircling a dark center, what is interpreted as the shadow of the event horizon. This image confirmed key predictions from general relativity and represented a historic leap forward in our grasp of black holes. Beyond black holes, event horizons hold great significance in cosmology. They serve as testing grounds for the boundaries of physics, helping us explore the relationship between space-time, gravity, and information. By studying what happens near these cosmic limits, researchers hope to uncover new knowledge that might eventually bridge quantum mechanics and general relativity. Interestingly, the event horizon could even have implications for the far future of the cosmos. As the universe continues to expand and galaxies drift apart, more and more objects may disappear beyond the event horizon of the observable universe. From a far-off perspective, our universe could eventually resemble a black hole sealed off, with no information escaping from beyond its outermost boundary. This so-called cosmic event horizon would mark the ultimate frontier of space-time, where nothing, not even light, could reach beyond. Ultimately, the event horizon represents the edge of our understanding. It's a reminder that certain parts of the universe may always be hidden from us, beyond the reach of our tools and theories. Yet, ironically, by studying this boundary, we come closer to grasping the deepest truths about reality. In exploring the outer limits of black holes and spacetime, we confront the very architecture of existence. The event horizon, with all its baffling qualities, stands as a symbol of the boundary between what we know and what still lies beyond, a place where science meets mystery and where the greatest discoveries may yet await.